Okay, so in order to understand electrolytic cells, we need to actually go back to the very early things that we learned in this chapter. So in the very beginning of this chapter, we learned about the galvanic cell. On the slide, you can see this is actually a very standard galvanic cell. So you have two solutions. Inside, you have your electrolyte. And then these two electrolytes was connected with your anode and cathode or electrodes. And then you connect the two electrodes with a wire. Inside the wire, you put a voltmeter, and then between the electrode solution, you put in the salt bridge. So under this case, basically the reaction is going to happen spontaneously, right? You are going to generate electrons. It goes from your anode, okay, to your cathode. So the things we're going to learn today is that instead of doing this, let the things happen spontaneously. I want to actually reverse everything. So what I really do is actually I'm going to replace my voltmeter with a big battery. So when I put a big battery here, I'm going to actually reverse the reactions. So once you reverse the reactions, then the things is going to start to deposit on the electrodes. That process is so-called electrolysis. So because of that process, it doesn't really need to actually separate these two things anymore, because all you have just a simple containers with all your reactants inside one single beaker. So in reality, when you actually look at your electrolysis cell, what you're going to have is actually you have all your electrolyte that are going to put inside one single beaker. So for this case, let's say you have your zinc 2 plus, copper 2 plus. Those things actually existing inside your solution. You will still need your electrodes. And then right now the electrode was connected through a wire, but again, you put a big battery inside. The electron was actually generated from this battery. So electron is going to be generated from your battery, and it goes into your solutions. Once the electron goes to your electrodes, since the electron is moving to here, the cation is going to move toward to this source, and then they're going to compete for the electrons. These cations inside your containers, okay, they're going to move to the electrodes and deposit on the electrodes. They are going to get reduced. Once they reduce, they are going to form actually a current, okay, and complete the loop. So let's actually the basic setup of an electrolysis cell. Okay, so eventually, that's what's going to happen. So once electron move to here, so you can expect on this specific electrodes, it's going to undergo a reduction reaction because the cation is going to receive the electrons. Then they are going to get reduced. If it's gain electrons, it's undergo reduction. These things will call the cathode. Under the electrolysis cell, the reduction still happen at your cathode. The new things is that your cations inside your solution, for example, your copper 2 plus or zinc 2 plus in this case, they will actually move toward the cathode. Cations is going to move to cathode, and the anions move to anode. So this is something that's unique in the electrolysis cell. Of course, inside these solutions, they are going to have some anions. So assuming you have fluoride or chloride anions here. Because right now, all the cations actually moving to your cathode. Okay, so you actually push your anions to the other side. These things are going to lose electrons. So your anions is undergo a oxidation reaction. Then it's going to produce the Cl2 and F2 to complete this electric circle. Previously, we say copper 2 plus got reduced. You become copper solid, so you got 2 electrons. Okay, and here is actually your zinc lost 2 electrons, become zinc 2 plus 2 electrons. So this is actually the galvanic cell. We know the E naught cell is actually positive 1.1 volt. But right now, when we do the electrolysis cell, you're actually trying to push the reaction in the reverse order. In other words, in the electrolysis cell, you're going to push copper solid become copper 2 plus 2 electrons. And then zinc 2 plus, now to gain 2 electrons to get your zinc. So when you do this, you can see that the E naught cell is going to equal to negative 1.1 volt. Because you reverse the reactions, so your E naught cell also changes signs. So you see a negative values of your electrolysis cell. If you just have galvanic cell, this reaction will happen spontaneously. Copper 2 plus become copper solid, or the zinc become zinc 2 plus. This thing will happen spontaneously if you have galvanic cell. But right now, what we really do is actually we want to reverse the reaction. So by doing that, now your E naught cell becomes negative. That negative sign means you can only make it happen when you provide a battery that have higher volt than that. So if this one is actually, if the voltage differences between your battery is larger than your E naught cell, then you can actually drive the things backwards. So you can have the electrolysis to happen. For the electrolysis cell, you always see your E naught cell is actually a negative value. Okay, and that negative value represents the minimum voltage that your battery need to provide to drive the electrolysis steps. One type of question you're going to get asked a lot is predict the product of electrolysis. So the rule of thumb is actually the cation always going to form at the cathode. The anion is going to form at the anode. So the first type of solution is actually the molten salt. For example, if today you're trying to isolate your sodium and the CO2 by doing electrolysis of the molten NaCl, we are going to have electrolysis cells. We have two electrodes connect with electric wire and batteries. And inside this solution, all you have is sodium plus, chloride minus. It's molten. And because it's salt, it will exist in the ionic form. Once you have this molten salt, so the electrons will go from your battery into your electrolysis cell. This is actually where we're going to have the G-rock. It means this one is actually your cathode. On the other side, here will be your LoRa. Oxidation is going to happen, and this will be your anode. The cations inside your solution will actually move to your cathode, and the anion will move to your anode. Therefore, in the end, you will know at the cathode, what you're going to have is Na plus is going to gain electrons and produce the reduced sodium. At your anode, your chloride is going to undergo an oxidation reaction to produce your CO2 plus 2 electrons. So the overall reaction will be, okay, you want to balance the overall charge, right? So there are 2, there are 1, so you need to actually multiply your equation at the cathode. So you can add it all up. So in the end, you're going to have 2 sodium plus 2 electrons plus 2 Cl minus. That's going to give you 2 sodium solid plus Cl2 in the gas form plus 2 electrons. 2 electrons, they're going to cancel out. So let's actually the overall reaction you're going to have. Now you want to actually calculate your E naught cell. So here is the standard reduction path reaction. Because your sodium gain 1 electrons, it becomes sodium solid. So what you need to do is actually go back to that big chart and then looking for the sodium on the reactant side. So you should be able to see that sodium gain 1 electron becomes sodium. They will actually need you to supply at least 2.71 volt to make the things to happen. So you know your E naught for this reduction is negative 2.71 volt. How about the next one? The chloride minus become CO2. This is undergo a oxidation reaction. So you want to actually looking for the Cl minus at the product side of the half reaction. This one is actually the one you're actually looking for. So you know your E naught oxidation is going to equals to negative 1.36 volt. So your E cell in total is actually the sum of 2. That means 4.07 volt. What it really means, you need to actually supply 4.07 volt so they can actually drive the whole thing. So you can have the cations go to your cathode, anions go to your anode. So this value is actually the minimum voltage that your batteries need to supply. The second and third type is like more complicated. But the basic principle, okay, is that In the second type solution, what you're going to have is actually going to have multiple melted salt. That means actually you're going to have multiple different cations and anions. You will ask you, okay, among those different cations, which one will form first? Which one will actually form at the least voltage supply? And then the same thing, which anion is going to form at your anode? To answer those questions, the rules you need to use is actually that if you have a cations, it has a less negative E naught value, okay, and less species will get reduced first. The same thing applied to your anion, okay? The anion with less negative E naught oxidation values, it will get oxidized first. Let's give you some examples so that these things maybe become more clear. Predict the product of electrolysis of molten mixture of sodium chloride and the aluminum fluoride. What are the cations in this molten salt solution? We can see that in the first one you got sodium plus, and then in the second one you got aluminum 3 plus. And then for your anions, you should see that you have Cl minus and the F minus. So once you see this, then you need to actually find out the corresponding reduction potentials and the corresponding oxidation potential. So let's look at the sodium plus and aluminum 3 plus. Reduction potentials, look at the reactant side. Okay, you want to looking for the sodium plus, which is this guy, right? It's negative 2.71. Negative 2.71. For your Al3 plus will be this guy, right? Negative 1.66 volt. So for your aluminum 3 plus, you only need to apply 1.66 volt. Okay, but for your sodium, you need to actually apply 2.71 volt. Based on that consideration, you know this is actually the one that's going to get reduced first. Then using similar principle, you want to looking for the Cl minus and the F minus. So if you look at the Cl minus, it's this guy, right? So let's actually reverse reaction. So you know the E naught ox is negative 1.36 volt. And then for your F minus, this guy, right? That means you need to provide 2.87 volt to drive the oxidation of your F minus. So once you get these values, the answer should be this, right? In the end, you know the overall reaction should be actually a combination of this. Al3 plus is going to get reduced, become Al solid, and then your E naught is equals to negative 1.66 volt. For your oxidation is actually 2Cl minus is becoming Cl2 plus 2 electrons. And then your E naught oxidation is negative 1.36. So the overall reaction is that you want to balance the charge. So you want to multiply 2 for the first equation, multiply 3 for your second equation. So in the end, you have 2 aluminum 3 plus 6 electrons plus 6 Cl minus. That's going to give you 2 aluminum solid plus 3 Cl2 gas plus 6 electrons. Okay, and 6 electrons cancel out. So this will be your final balance equation. In that cell will be actually the sum of 2. So that will equals to negative 3.02 volt. So you need to actually apply 3.02 volt to complete the electric circle so that your aluminum will get reduced, your chlorine will get oxidized to form the Cl2. With that in mind, let's look at another example. Consider a solution containing 0.1 M of all these different species. You have multiple molten cations here. Predict the order in which the metal plate start to actually form, okay, when the voltage starting turning up from 0. So again, apparently this is actually the things that you know is undergo electrolysis reactions, right? So you want to actually know what is your E naught for each species. So here you have Pb2 plus, Cu2 plus, Sm2 plus, Ni2 plus, and then your Zn2 plus. The first thing you do is actually you want to actually check out your standard reduction potential table and then pull out the numbers. So assuming I pull out all the value for you, so this is actually negative 0.13 volt. This is 0.34 volt. This is negative 0.14 volt. And then negative 0.23 volt. And then negative 0.76 volt. So those are the standard reduction potentials. With this information, we know that the kaons with the less negative standard reduction potential will get formed first. So based on that principle, which metals will actually form first? I guess you got a little bit confused, right? Because we have a positive value here. So what does positive value means? The positive value means actually it's going to happen spontaneously. If your E naught cell is actually positive, that means actually it's going to happen spontaneously. You don't need to even apply the voltage. Therefore, they will be actually the first guy who got deposit on your cathode. Who will be the second one? Lead. Okay, so lead is the second one. Third one. Fourth. Okay, so this will be the fifth one. Therefore, you know, when you start to turn on the voltage, you follow these orders. And all this Ki will deposit on where? Cathode or anode? Ki goes to cathode, Anion goes to anode. Okay. So let's actually the things that you will need to actually know how to address it. Let's go to the very last solution. The solution contains waters. Water itself is actually a very unique molecule. It can undergo either the oxidation or reduction. So here I list the standard reduction potential of your H2O and the standard oxidation potential for the H2O. Okay, so one is negative 0.83, the other one is actually next 1.23. If the water undergo a reduction reactions, it produces H2. If undergo an oxidation reaction, it produces O2. You need to actually memorize these two equations. Once you know this, the principles we learned so far, they all apply. So you want to find out if you have multiple salt together with your water, and then you consider all their standard reduction potential or their oxidation potential. The one with the least negative values is going to be the one that got electrolysis. So this is an example. We did a product of the electrolysis of a mixture of 1N sodium chloride AQ and 1N KNO3 AQ, okay, with inert electrons. So this is actually the thing that you need to see. No water is actually need to be considered. Be very careful. If you look at this equation, it says AQ, okay, in the electrolysis process that belongs to the solution type 3. So again, you're going to actually analyze your system. What are the kaons? What are the anions? Because we see AQ, you know I need to consider water in both cases. And then I analyze my kaons. I know from here I have sodium plus. From here I have K plus. For the anions, I know I have Cl minus and the NO3 minus. So one of this is going to form the product at the cathode. One of this is going to form the product at the anode. All you need to do is actually find out what is the E naught for these three. And then in this case, you want to find out the E naught oxidation of these three. For water, the standard reduction potential is 0.83 volts. For the oxidation, is actually negative 1.23 volts. Then the next thing is actually, again, you need to go and check out your table. Then you'll find out your sodium plus is negative 2.71, and then potassium is actually negative 2.93. And again, you can also check out the E naught oxidation for your Cl minus, which is negative 1.36 volts. When you check out the oxidation potential for your NO3 minus, typically you won't be able to see it on the table. The reason it is actually not on the table is simply because they cannot be further oxidized. So you're going to see NO3 minus or the SO4 2 minus. If you see the species is relatively complicated, like multi-atom species, it won't be your answer. So just ignore it. Okay, so right now you actually got the things sold out. You want to pick the one with the less negative values, and there will be actually species undergo your reduction. Okay, in this case, it will be your water. And then when the water is actually got reduced, the hydrogen gas will be the product. So you're going to see the hydrogen gas forming at the cathode. Similar things for your NOx. H2O has the less negative values. So the H2O will actually undergo an oxidation reaction, and it's going to produce O2 gas at the anode. And then the E NOx cell will be the sum of these two, which is going to give you negative 2.06 volt.